so on section 6.1, looking at number 21. And we have an integral to deal with. So it's cosine squared x dx. And the hint they gave us was to replace that with 1 plus cosine 2x over 2 dx. And ultimately, with that, we can rewrite the integrand as 1/2 plus 1/2 cosine 2x dx. They're both divided by 2. We can separate that into 2 separate parts. And ultimately, if we do antiderivatives here, the antiderivative of 1/2 should be 1/2 x. And the antiderivative of cosine 2x, again, we're going to pull the 1/2 out first. The antiderivative of cosine 2x would be sine 2x over 2. Alright, and so ultimately we get 1/2 x plus 1/4 sine 2x plus c. And that would do it. Okay.
Why is it sine 2x over 2?
Because in general, what's our rule that we have in our previous page? Sine kx is cosine kx, that is. If I have cosine kx, it's 1 over k sine kx. Get my k's and my x's straight here. So, and again, it comes from our differentiation rule. If I were to differentiate just this part right here, sine 2x, I'd get cosine 2x times 2. Is the chain rule? True? So if I got cosine 2x times 2, and I multiplied it by 1/4, what would we be back to? We'd be back to 1/2, wouldn't we? So, anything else on that one? Others from the book?
Can you do number 19?
And 19, we got 5, which I'd pull out immediately here. We got secant squared of 5r dr. And ultimately, thinking along those exact same lines that we just did with this cosine problem, if this was just secant squared r, our answer would just be tangent r. Okay? But since it's secant squared 5r, okay, there's a chain rule issue. So we can't just put tangent 5r. Okay? Just like we do for sine and cosine, we'd have to divide by the 5, just like we did up here. Okay? So ultimately it would be 1/5 tangent 5r plus c. Keep in mind we had a 5 out in front. You got to put the 5 back in there. Okay? So ultimately we would wind up with, in fact, tangent of 5r plus c. Again, just like our sine and cosine rules, if I have secant of some other argument besides just plain old r or x or whatever the variable is, we have to account for the chain rule by dividing by that derivative inside.
Yeah, I'd rather pull 5, that's why I like.
Okay. Alright. Others on that one? Alright. Others from the book? How about from our slope field worksheet? Problems drawing or matching or etc.? Sure. Should be the one set I already had there, but the second page on there, which should be number 7 should be D. Number 8 we said already was H. Number 9 should be C. Number 10 should be F. Number 11 should be A. 12 should be E. 13 should be B. And then 14 should be G. Questions? Anything on the matching part on that page? else in the slope field worksheets? Where it's dy dx equals 2y.
No, I meant third.
So x plus y. So if I have dy dx equals x plus y, and I'm going to draw a slope field for it. Ultimately, again, if I you can start really wherever you want to here. Bottom line, you got 0, 0 here. If I were to put 0, 0 into x plus y, I'd get 0. So would my segment be a horizontal line there? And then if I go 0, 1, 0 plus 1 would give me a slope of 1. 0 plus 2 would give me a slope of 2. 0 plus 3 would give me a slope of 3. So ultimately, they'd be going up in slope as we went up the line there. Okay. And then if I go 0, negative 1, I'd go 0 plus negative 1 would be negative 1, so these would be going down over here. Negative 2, negative 3, so on. And then ultimately we do the same thing here. If I did 1, 0, that would be 1. If I did 1, 1, that would be a little steeper, it would be 2. If I did 1, 2, it would be 3. So ultimately we're adding those two coordinates together to get the slope. Okay? And so ultimately we just fill in the blanks on all the rest of those, and when we get done, we'd have a slope field. What else? Alright, just to make sure that we're clear on a couple of things here, just to make sure we saw some patterns here when we did the pictures. Ultimately, when we have our pictures of our slope fields, we'll look at these that are already done for us. Notice in number 15, which matches up with letter B. Okay, notice that as we go down the columns, okay, what do we notice down the columns for all the marks? They all have the same what? They all have the same slope. Okay, you should have noticed that that happens anytime that the dy dx is just in terms of x only. If it's in terms of x only, you should have symmetry as you go down the columns. It should be exactly the same slope as you go down the column. Okay, if you look at number 16, which corresponds with letter D, that's not the case here. Notice they're all different slopes as we go down the column, but what happens when we go down the rows? They're all the same. So there's ultimately similarities here in our rows when we have in terms of y only, instead of in terms of x only. And you notice that 17 and 18, if you look at A and B, is there any commonality in the rows or columns for either one of those? No. Okay. So those are both in terms of x and y. So bottom line is, if this were a problem on the AP test and you had to decide which one went with which, for instance, I mean, automatically you could look at this one right here and see that it's the same down each column. And you could rule out both 17 and 18 because there's no way those could be like that. They're in terms of both x and y. The only way I can have the same slope in every column, okay, is that if it's in x only. Okay? Same thing with the rows. If I see that it's in rows, same for each row, then it has to be in y only. Okay? So ultimately you could save yourself some time by ruling out two of those right off the bat, couldn't you? And if you see one that looks like this where there is no similarity in rows or columns, then you could rule out these two because there's no way it can be those. It's got to be one of these two. Okay. So hopefully that pattern was evident on the pictures you drew on the first page as well. All right. Anybody have any questions about anything they read about in the AP problems that I gave you? Discuss anything further with those? They're in your packet. Yeah. So like on this one, for instance, we had again, keep in mind that this was a legitimate slope field problem here. It says on the axes provided, sketch a slope field for this differential equation. So really, is that any different than what we did on page 1? Okay. So in the scheme of things, that's worth only 1 point. Shouldn't be terribly surprising since it's a pretty easy question if you know how to do a slope field. Okay. So, and then you'll notice that in 2000 we had the same deal. Just had to draw a slope field for that differential equation. This one was actually worth 2 points, which is nice because, like I said, in the scheme of things, it's fairly easy, 2 points, to be able to draw those slopes. Okay. And then we had a little different problem in 2002. Okay. We had to be given the slope field, and we had to sketch the solution curve that passes through 0, 1. So again, if you look at 0, 1, all the slopes are going in that direction that they've drawn that line. And so again, our job is just to draw that curve as we see. Okay? If it goes through 0, negative 1, okay, look at what the trend of the curves is going through negative 1. You plot that point, and then you just draw as you see fit going through those curves. Notice it goes up here and then back down, because again, what do the segments do near that point? Okay. To the left of it, they're going up and around, if you will, and then down as we go to the right. And so we would just sketch that curve, and that would do it. Okay. So there'll be some more problems where we practice on drawing curves on slope fields as we go through this as well. All right, so with that, let's go ahead and work on next, or part 2 of this section, which, as I mentioned yesterday, is going to be dealing with some more differential equations. And let's take a look at a couple examples here. So let's see, number 1, we're going to call it, we're going to say that our dy dx equals sine x. Okay. And ultimately, what we want to do with that is solve this differential equation. So in general, we need to make sure we understand what does it mean to solve a differential equation. Okay? And if we're given some equation that has a derivative in it, remember we said yesterday that that is a differential equation. Okay? And so for us to solve this differential equation means for us to figure out what function did this come from. Fair enough? And so in this case, it's a really fairly simple problem, because we know that if dy dx is sine x, then y must have been what? Negative cosine x plus what?
C.
Plus c. So just by inspection, we can figure out what that one is, because that's a known derivative. That's a pretty easy problem for us to figure out. Okay. Now, they're not all like that, of course, as you can imagine. So we're going to do a technique here that we're going to use with essentially all differential equations that we're able to solve. And the reason that we're able to solve this is because we call this a separable differential equation. Okay, and so our first step in solving any differential equation is going to be to separate the variables. Okay, so we're going to separate the variables, and this is what I mean by that. We're going to get anything that has x on one side, and we're going to get anything that has y on the other. Okay, and keep in mind that just like when we did differentials in the previous chapter, okay, we can rewrite this sentence as dy equals sine x dx. Okay, we know that those two sentences are equivalent based on what we did with differentials. Okay, so once we write it like that, then the part that has an x in it and the dx are together, and the part that has a y, which is essentially just 1 at this point, and if you want to write 1 in front of that, you can if you want to, it's up to you, but bottom line is we just have 1 dy on the left. Okay, so again, we don't really need this technique for this particular problem because it's a simple one, but bottom line is this is what we're going to do for all. We're going to separate the variables. That's step 1. Step 2 is we're going to integrate both sides. Okay, and ultimately, if we integrate this side, we integrate 1 dy, we're going to get what? The antiderivative of 1 is going to be what? Okay, 1 dy. That's y. So again, the independent variable is important there. It's 1 dy, so therefore it's y. And the antiderivative of sine x here is negative cosine x plus c. And so ultimately, what did we wind up with? The solution to the differential equation. Now, the one issue that we'll sometimes have here, and we don't have it in this case, is that when we actually do the integration, that y is not alone. So there might be another step here where we have to figure out what y is equal to by solving the equation for y. Okay, so we'll see that in a minute when we do a little bit more. All right. So ultimately, again, to repeat, our solution to a differential equation is just what function did this come from. Okay, and so our general strategy is to separate the variables, integrate both sides, solve for y. Okay. So now, what makes this this problem a little bit different is if they had given us in the first place, if they had given us an initial condition. So let's say they said that dy dx equals sine x. We'll stick with our simple example here. and we know that y of 0 equals 2. So we know that not only do we know what the derivative of the function that we're looking for is, okay, we know the derivative, we just need to find the function, but we also know that a point that the function goes through, which ultimately is going to allow us to do what? How is that going to do anything different for us? It's going to be able to give us means to find c. So if we do our same work, and I'll skip the work part for the time being since we already did it. So we'd have that. And one thing that we want to get in the habit of doing is as soon as we anti-differentiate both sides, okay, we need to plug in the initial condition now. Okay? In this case, the y is already solved for. In some cases, as I said, it's not already solved for. But either way, whether y is alone or not, okay, put in the initial condition now. Okay? Don't solve for y first and then put in the initial condition. So with that, we'd have 2 here. We'd have negative cosine of 0 here plus c here. And so if we do cosine of 0, we know that's 1. So we'd have negative 1 plus c, and ultimately we get 3 equals c. And so then our final answer of the new problem that I've posed here is negative cosine x plus 3. Okay? And so keep in mind that first solution that we got is the solution to the differential equation dy dx equals sine x. Okay? This is the solution to the initial value problem where dy dx is sine x and the initial condition is y of 0 equals 2. Okay, so that's the difference between the two problems. This is just solving a differential equation. Okay, this is solving an initial value problem. So how do we know which one's which? Well, if they give you just a differential equation and no initial value, then you wouldn't be able to do this part, would you? Okay, so that's the difference. If you got an initial condition given, then you can actually find c and come up with an exact equation for the solution. Okay, questions so far? All right. Let's look at another one here. We're going to look at the differential equation dy dt equals 0.056y. All right. And this is kind of an interesting one because this is going to look familiar when we get finished with it. If you what it boils down to is this particular differential equation, when I have the derivative here being proportional to the amount, if you will, okay, that ultimately gives us a certain kind of differential equation, which we'll see, like I said, in just a minute. Bottom line here is that, I guess I'll save that for a minute because then we'll get to the other part of the explanation in a minute. So we have dy dt equals 0.056y. And so ultimately, the y part needs to be with the y part, and that t part needs to be with the other part. Now, here's what I would do. My technique on this would be every time is that if I have 0.65y, I would divide by y only. I would not divide the 0.56 over to the other side. Okay? It's going to be much better to have 1 over y because we know the antiderivative of that is going to be natural log y. Fairly simple to calculate. Okay? And we can leave the 0.056 over here because, again, to get rid of y, we're just dividing by y. Okay? And if we divide the left side by y, we do that and get 1 over y, etc. And then at the same time, okay, I'd multiply both sides by dt. That means that we'll have 1 over y dy, and then 0.056 dt. Okay? Now, we were also given an initial condition in this problem. And if you want to look with me here on page 304. Okay. The initial condition here is that at time 0, my y is equal to 100. So we'll bring the finance part into this in just a few minutes. But bottom line here is if we are given this differential equation and this initial condition, and we separate the variables, step 1, and then we anti-differentiate both sides, we would have the following. We'd have natural log of absolute value of y on the left. We'd have 0.056t plus c on the right. And ultimately, again, we're looking for the equation this comes from. We're looking for y here, but we don't want to solve for y yet because it's not time to solve for y yet. We want to find the value of c first. Okay? And I'm going to tell you right now that the book doesn't always do that. So if you look at the way the book did it, they don't find c first. And ultimately, I've found that if you find c first, you run into a lot less problems. Okay? So my suggestion is that you find c first, regardless of whether the book does it or not. So ultimately, we'd have ln of absolute value of 100, and 0 in there would just give us c. So we could find c, and then our equation then would be natural log of absolute value of y, 0.056t plus ln of 100. We don't need the absolute values on 100 because 100 is positive already, so we can just disregard the absolute values there. Okay. All right, questions on steps so far?
Why is the L and 100 equals C separate?
I put 100 in here and 0 in here to solve for C. We're putting the initial condition 0, 100. And ultimately we're just solving that for C. And now that we have C, we can rewrite the equation with our C in the right spot. Alright, and then from here, now once we've gotten the C taken care of, now we need to solve this for Y. So if we solve this for Y, we're going to get a composition with E here. This is the way we get rid of the natural log. And so if we compose both sides with E, that's going to give us Y here. And then on the right hand side, we're going to have e to the 0.056t plus ln 100. And so that ultimately would be our equation, solve for Y. Now, we don't want to leave it like this though, because ultimately there's something we can do here, especially when we have an e and a natural log here. But remember, the technique is this: the algebra that we've done in the past and will continue to do is going to be to rewrite it with our laws of exponents. Okay? Our laws of exponents say that if we multiply e together like this, that we add the exponents. So instead of having the added exponents, can we go back to the original form and have e to the first times e to the second? Of course, the answer is yes to that. And then when we get done here, our answer is going to be this right here is simply 100. And so we get 100 times 0.056 e to the 0.056t. Okay? And if you look at that equation, okay, and we put it in the context of the problem that was given, remember our formula for continuously compounded interest was a times e to the, there's a equals p times e to the RT. And ultimately, here's my p that I put in, $100, right? Base e. Here's my rate, 5.6% interest rate, and here's our time variable. Okay? So ultimately, this continuous compounding situation, okay, stems from the fact that the rate of change is dependent upon the amount. Okay? And so anytime we have a differential equation that is some rate times y, okay, we're going to wind up with this model when we get finished. We're going to wind up with a equals p times e to the RT.
What's that big in front?
A. So, like I said, anytime we have this type of differential equation to start with, where it's some number times y, dy dt equals some number times y, okay, all the work is going to be exactly the same. And the number is the only thing that would be different. We're going to always wind up with something of the form p times e to the RT. Right? So again, this type of differential equation is important because it shows up in a lot of applications. We have a lot of continuous compounding situations, continuous growth situations, continuous decay situations, that this type of differential equation leads us to that equation. Okay? So there might be other ways to do it, but ultimately, we've shown that this equation, a equals p times e to the RT, just isn't like a magic equation that works because the teacher said so. True? Okay? So, because what did we do when we solved this differential equation? What did we get? We got exactly that, didn't we? Okay. All right. Let's take a look at one more example here of using our technique here to find the solution to an initial value problem. If you look at your homework assignment page, that's page 313. In our work for today, if you will, the say number 34, for instance, we have dy dx equals 1 over x, and then it says y of e to the third equals 0. So that being our initial condition, that being our differential equation. Our issue here is can we come up with an answer here? And you'll notice that in your homework assignment today, all the ones that you need to do are relatively easy because they all just have x in them and no y's. We're going to do some that are a little more difficult in terms of that variable separation part later. But ultimately, if I do my technique that we just learned, we would separate the variables, and dy dx would equal 1 over x dx. And then from there, we would integrate both sides, and we get y over here, and we get ln absolute value of x here, plus c. And then from there, we'd plug in the initial condition. We get 0 here. We get ln of e to the 3 here, plus c. Keeping in mind that ln of e to the 3 here is 3. So we'd ultimately wind up with -3 being our c. Remember, natural log of e to the x is just x, because those two are inverses of each other, so they undo each other and give us the argument. And so with that said, we'd have y equals ln absolute value of x minus 3. And ultimately that would do it. Okay? That's really our only job, is just to solve the differential equation, solve the initial value problem, that is, because if it was just solve the differential equation, we would have stopped right here. Okay? But they gave us an initial value, so that means plug in the initial value, figure out what c is, and then our final answer is this. And again, keep in mind that what we're finding here is an equation, okay, that if we were to differentiate it, we'd get this. And if we were to put e to the 3 into it, we'd get this. Okay? This right here satisfies both of those conditions, doesn't it? Okay? If we differentiate this, we'd get 1 over x. If we put e to the 3 in here, we get 3 minus 3, which is what? Which is 0. So again, ultimately what we've come up with is an equation that satisfies both of those things. It satisfies the fact that the derivative is correct, and it satisfies the initial condition, which means if we put e to the 3 in there, we get 0. Yep.
What about like number 35 when they give you the second derivative?
Ultimately, if we have the second derivative, then we're going to have to do this how many times? Okay. If we anti-differentiate, we'd get dy dx, wouldn't we? Okay. But again, keep in mind, if we do that, okay, it's going to have a c involved, true? But we'll notice what information did they give us? They gave us the value of the derivative at a point, didn't they? So we could find c, and once we got done, we'd have an equation like this, but instead of y, it'd be dy dx. And then ultimately, what are we going to do with that dy dx equation we just found? We're just going to do it again. So ultimately, you just have to do it twice. All right. So the final problem I want to look at here, though, is number 40. It's an example problem. And it says here that the v is equal to sine of pi t, and s of 1 is 0. So we have a v equation here, which is a velocity. It might be an acceleration problem, possibly. And the bottom line here is that we want to find the body's position s at time t. So we want to find the position equation if we're given the velocity equation. So really absolutely no different than what we just did, because the velocity is the derivative of this position that we're trying to find. If we had the acceleration, we'd need to do it twice again, wouldn't we? Okay, we need to get back to position. So with that, what would be the antiderivative of sine pi t? It would be negative 1 over pi cosine pi t. We follow our rules that we know. And of course, that's plus c. And if we know that the initial condition here is 1, 0, then we can plug in 0 and 1. And cosine of pi is negative 1. Okay. And so therefore negative 1 times that would be that. And ultimately we go 1 minus pi, or minus 1 over pi, that is, and get our c. And so our final answer for the position function here then would be negative 1 over pi cosine pi t minus 1 over pi. So ultimately, even though it was in the context of velocity and position, did any of the rules change? Did we do anything different than we did in the previous problems? Exactly the same thing. Questions so far?